Close your eyes and imagine yourself floating in the most peaceful place imaginable. You're weightless, suspended in perfect stillness, wrapped in gentle silence. Around you, the curved walls of your sleeping quarters glow softly with ambient light, just enough to see the gentle texture of the fabric that holds you in place. Outside your window, Earth turns slowly beneath you, a massive sphere of deep blues and swirling whites, lit by the sun's golden rays. There's no rush here, no urgency. Time moves differently in this place, measured not by the frantic ticking of clocks but by the slow, graceful orbit of your spacecraft around our home planet. You feel your breathing slow, matching the rhythm of this serene environment. The gentle hum of life support systems creates a soothing background, like a lullaby from the machines that keep you safe and comfortable. This is space travel, and tonight, as you drift towards sleep, let me share with you the most calming, most peaceful aspects of humanity's journey beyond our atmosphere. Let these gentle truths about space exploration carry you into the deepest, most restful sleep. The dawn of space travel, from dreams to reality. Long before any rocket lifted off from Earth, space travel existed first as a dream, whispered between people who looked up at the night sky and wondered what lay beyond. These dreams were quiet and persistent, passed down through generations like a comforting bedtime story. In the early 1900s, a Russian schoolteacher named Konstantin Tsiolkovsky spent his evenings imagining rockets that could carry people to the stars. He never built these vessels, but he wrote down his ideas with careful, methodical detail, solving problems on paper that wouldn't be confronted in reality for decades to come. There was something deeply peaceful about his approach, working alone in his quiet study, calculating trajectories and fuel ratios while the rest of the world slept. Tsiolkovsky understood that reaching space would require patience and careful planning. He realized that rockets would need liquid fuel instead of solid propellants, providing a smooth, controlled burn that could be adjusted during flight. He conceived of multi-stage rockets, where sections would gently separate and fall away once their fuel was spent, reducing the mass that needed to be pushed forward. These weren't violent explosions but carefully choreographed separations, each stage doing its job before peacefully releasing its hold on the next. The mathematics he developed described elegant curves through space, paths of minimum resistance where a spacecraft could glide along invisible rails laid down by gravity and momentum. Across the Atlantic Ocean, another quiet dreamer was pursuing similar visions. Robert Goddard, an American physicist, spent his days teaching and his spare hours building actual rockets in his workshop. In 1926, he achieved something remarkable in a snowy field in Massachusetts. His liquid-fueled rocket rose into the air for just 2.5 seconds, traveling a mere 41 feet before settling back to Earth. But in those brief moments, Goddard had proved that controlled rocket flight was possible. The launch wasn't a thunderous spectacle, but rather a small, almost gentle demonstration of principles that would eventually carry humans beyond the atmosphere. Goddard continued his work with methodical care, testing each component, measuring every result, gradually improving his designs. He worked in relative obscurity, away from public attention, finding satisfaction in the steady progress of his experiments. His rockets grew taller and flew higher, each flight teaching him something new about stability, guidance, and control. There was a meditative quality to this incremental advancement, each small success building upon the last, like stones carefully stacked to create a stable foundation. In Europe, Hermann Oberth was pursuing the same dream with Germanic precision and thoroughness. He published detailed technical papers describing how rockets could work in the vacuum of space, where there was no air to push against. Many people assumed rockets needed air to function, but Oberth explained with calm logic how Newton's third law, action and reaction, would work even better without atmospheric resistance. A rocket doesn't push against air. It pushes against its own exhaust, and in the emptiness of space, that exhaust can flow freely, creating smooth, efficient thrust. These three pioneers, working independently across different continents, were all pursuing the same gentle dream. None of them sought fame or fortune. They simply wanted to solve the puzzle of spaceflight, to show that humans could leave Earth's surface and touch the cosmos. Their work created the foundation for everything that would follow, and they approached it with patience, careful thought, and a quiet determination that never wavered. When World War II ended, the world inherited German rocket technology that had been developed during the conflict. These V-2 rockets had reached the edge of space, climbing to heights of over 100 miles before falling back to Earth. In 1942, one of these rockets became the first human-made object to cross the boundary into space, that invisible line 100 kilometers above sea level where the atmosphere fades to nothing. After the war, both the United States and the Soviet Union gathered German rocket scientists and their technology, beginning programs that would eventually lead to the space age. The competition that followed, known as the space race, is often portrayed as frantic and adversarial, but within it were moments of profound peace and achievement. On October 4, 1957, the Soviet Union launched Sputnik, the first artificial satellite to orbit Earth. It was a simple sphere, about the size of a beach ball, weighing 184 pounds and covered in polished aluminum that caught the sunlight as it circled the globe. Every 96 minutes, Sputnik completed one orbit, traveling in a gentle ellipse that brought it as close as 142 miles and as far as 588 miles from Earth's surface. The satellite transmitted a simple radio signal, a steady beeping that could be picked up by anyone with the right equipment. People around the world tuned in to listen to this electronic heartbeat from space, a sound that represented humanity's first successful step beyond our planet. The beeping wasn't urgent or alarming. It was calm and regular, like a pulse confirming that our creation was alive and well in the heavens. On clear nights, observers with binoculars could even see Sputnik as it passed overhead, a tiny point of light moving steadily against the fixed stars, proof that humans had placed something permanent in the sky. The United States responded with its own satellite program, and on January 31, 1958, Explorer 1 reached orbit. This satellite was packed with scientific instruments designed to measure conditions in near-Earth space. Its most significant discovery was the Van Allen radiation belts, regions where Earth's magnetic field traps charged particles from the sun. This finding wasn't planned. It emerged from careful analysis of the data Explorer sent back, showing that space held surprises waiting to be discovered through patient observation. These early satellites had peaceful purposes. They were designed to study space, not to wage war. Sputnik 3, launched in May of 1958, carried instruments to measure atmospheric pressure, composition, charged particles, cosmic rays, magnetic fields, and even the presence of tiny meteorites. Each piece of data it gathered helped scientists understand the environment beyond our atmosphere, knowledge that would be essential for keeping future astronauts safe. The satellites orbited in silence, gathering information, sending it home in steady streams of radio signals, asking nothing but to be allowed to continue their quiet observations. As the 1950s gave way to the 60s, the space race intensified, but it also matured. Both nations realized that sending humans into space would require extraordinary care and preparation. Spacecraft had to be designed not just to reach orbit, but to keep their occupants alive and comfortable in an environment fundamentally hostile to human life. This challenge demanded cooperation between engineers, doctors, physiologists, and countless other specialists, all working together toward a common goal. The complexity of the task forced a methodical, thoughtful approach. There was no room for haste or carelessness. Every system had to be tested and retested, every contingency planned for, every risk carefully weighed. In 1961, Yuri Gagarin became the first human to orbit Earth, completing one circuit in 108 minutes aboard Vostok 1. His flight was brief, but it proved that humans could survive in space, experiencing weightlessness and high acceleration without harm. Gagarin described the view from his window, looking down at Earth's curve against the black void, seeing the thin blue line of atmosphere that separates our living world from the emptiness beyond. He spoke of the beauty and fragility of our planet, how it appeared as a precious sphere floating in darkness. And his words carried a message of peace and wonder that transcended the political tensions of his era. The Mercury and Gemini programs in the United States gradually extended the duration of spaceflights, testing equipment and procedures that would be needed for longer missions. Astronauts learned to eat, sleep, and work in microgravity. They practiced rendezvous and docking maneuvers, bringing two spacecraft together with delicate precision, matching their velocities to within inches per second before making contact. These operations required intense concentration and steady hands, but they were never rushed. Controllers on the ground worked through checklists with calm professionalism, and astronauts executed each step with patient care, knowing that precision mattered more than speed. Then came Apollo, the program designed to land humans on the moon. The goal was ambitious, but the approach remained methodical. Engineers built the Saturn V rocket, the largest and most powerful launcher ever successfully flown, standing 364 feet tall and capable of lifting 140 tons to low Earth orbit. Despite its immense power, the Saturn V was also remarkably reliable and smooth in operation. Astronauts described the launch as surprisingly gentle, a gradual building of speed and altitude rather than a violent jolt. The rocket's 5 main engines produced a combined 7.6 million pounds of thrust, but they did so with controlled, steady burns that lasted over 2.5 minutes before the first stage separated. On July 20, 1969, Neil Armstrong and Buzz Aldrin landed on the moon while Michael Collins orbited above in the command module. The landing itself was a moment of supreme calm under pressure. Armstrong, seeing that the automatic landing system was heading toward a boulder field, took manual control and guided the lunar module to a smooth touchdown with less than 30 seconds of fuel remaining. His famous words, "The Eagle has landed," were delivered in a steady, professional tone that belied the tension of those final moments. Then came the long wait before the first moonwalk, hours of preparation and checking before the hatch finally opened. Armstrong descended the ladder slowly, placing each foot with care, and when he stepped onto the lunar surface, he paused to describe what he saw. Fine-grained dust, the footpad of the lunar module resting gently on the surface, shadows that were absolutely black because there was no atmosphere to scatter light. Everything was perfectly still, preserved in the airless silence of the moon. When he spoke his prepared words about one small step and one giant leap, he was acknowledging both the magnitude of the achievement and the careful, incremental progress that had made it possible. The Apollo program flew 6 successful moon landings between 1969 and 1972, and each mission added to our knowledge of our nearest celestial neighbor. Astronauts collected rocks and soil samples, set up scientific instruments, and took thousands of photographs. They described the moon as peaceful and ancient, a world unchanged for billions of years, waiting patiently for its first visitors. When the last Apollo mission departed in December of 1972, the moon returned to its solitude. The equipment left behind the only evidence that humans had briefly interrupted its eternal quiet. Since those pioneering days, space travel has become more routine, though never ordinary. Thousands of satellites now orbit Earth, most of them performing quiet, essential tasks. Watching weather patterns, relaying communications, providing navigation signals, observing our planet's climate and ecosystems. They circle in stable orbits, requiring only occasional adjustments to maintain their positions, going about their work with patient reliability year after year. Some have operated for decades, far exceeding their designed lifetimes, testament to the care taken in their construction. The history of space travel is ultimately a story of patience and persistence, of dreams nurtured over generations and realized through careful, methodical work. It shows us that even the most ambitious goals can be achieved through steady progress, one small step at a time. As you rest tonight, imagine that same patient progress continuing, spacecraft quietly making their way through the solar system, gathering knowledge, extending the reach of human curiosity ever further into the peaceful depths of space. The serene science of spacecraft design. Every spacecraft that ventures beyond Earth's atmosphere is a masterpiece of careful design, created to function in the silent vacuum of space. Unlike the vehicles we use on Earth, spacecraft don't battle against wind resistance or rough roads. They move through emptiness, where the only forces acting upon them are gravity and the gentle push of their own propulsion systems. This fundamental difference shapes every aspect of their construction, resulting in vehicles that seem almost ethereal in their delicacy, despite the extreme environment they must endure. The vacuum of space imposes its own unique challenges, but it also offers surprising advantages. Without air, there's no drag to slow a spacecraft down. Once an object is set in motion, it continues moving at the same speed and direction indefinitely unless acted upon by another force. This means that spacecraft don't need constant thrust to maintain their velocity. Instead, they coast through the void like stones skipping across perfectly still water, following trajectories determined by gravity and their initial momentum. Propulsion is used only for course corrections and maneuvers, with engines firing in brief, controlled bursts separated by long periods of quiet drift. Spacecraft thermal control systems maintain temperature with elegant simplicity. Without air to conduct heat, a spacecraft in sunlight can become scorching hot on one side, while the shadowed side drops to hundreds of degrees below zero. To manage this, engineers design thermal control systems that use special coatings and materials. Surfaces can be covered with paints and foils that reflect sunlight or absorb it, radiating heat away into space as infrared radiation. These passive systems require no moving parts and no power. They simply work continuously and silently, maintaining equilibrium between the heat absorbed and the heat radiated away. For more active temperature control, spacecraft use loops of circulating fluid, much like the cooling system in a car but refined to perfection. Pumps move the fluid through channels in spacecraft walls and equipment, gathering waste heat and carrying it to radiators where it's released into space. The fluid flows in a closed loop, never needing to be replenished, circulating endlessly in a cycle as regular as breathing. The pumps and valves operate with quiet efficiency, their moving parts designed to function in the harsh environment of space for years without maintenance. The International Space Station provides an excellent example of these systems working in harmony. The station has massive radiators, panels that can be rotated to face toward or away from the sun as needed. When deployed, these radiators glow with the infrared light of heat being shed into space, invisible to the human eye but clearly visible in thermal imaging. The station maintains a comfortable temperature inside, typically around 20 to 27 degrees Celsius, creating a shirt-sleeve environment where astronauts can work without the burden of heavy protective clothing. This temperature is maintained automatically, with computers monitoring hundreds of sensors and making constant tiny adjustments to keep conditions optimal. Life support systems on spacecraft operate with similar elegance and reliability. The basic needs are straightforward: provide oxygen to breathe, remove carbon dioxide, maintain proper humidity, and ensure adequate air circulation. On the International Space Station, these functions are handled by the Environmental Control and Life Support System, a beautifully integrated collection of equipment that works continuously to keep the atmosphere healthy and comfortable. Oxygen generation is accomplished through electrolysis, the same process used in chemistry classes but refined to space-grade reliability. Water is broken down into its constituent elements, hydrogen and oxygen, using electrical current passed through it. The oxygen is released into the cabin air while the hydrogen is vented into space. This process is quiet and clean, producing a steady supply of breathable air without combustion or chemical reactions. The system can run indefinitely as long as water and electricity are available, both of which the space station has in abundance from its solar panels and water recycling systems. Carbon dioxide removal uses a different but equally elegant approach. As astronauts breathe, they exhale carbon dioxide that must be scrubbed from the air to prevent it from reaching dangerous levels. The system uses a material that selectively absorbs carbon dioxide molecules, pulling them from the passing airstream. Once saturated, this material is exposed to the vacuum of space, which causes it to release the collected carbon dioxide, refreshing it for another cycle of use. The process repeats continuously, maintaining carbon dioxide at safe levels without generating waste or requiring consumables beyond the initial adsorbent material. Humidity control ensures that the air doesn't become too dry or too moist, Water vapor is constantly being added to the cabin atmosphere through human respiration and perspiration, and it must be removed to prevent condensation on cold surfaces and maintain comfort. Condensers cool the air, causing water vapor to condense into liquid that's then collected and recycled. This water is incredibly precious in space, and the recycling systems can recover over 98% of it, purifying wastewater and humidity condensate to drinking water standards. What arrives at the space station as waste leaves as pure, clean water, closing the loop in a cycle that's both efficient and elegant. Air circulation might seem like a minor concern, but in microgravity, it's essential for survival. On Earth, warm air rises because it's less dense than cool air, creating natural convection currents that distribute heat and fresh air throughout a room. In space, there's no up for warm air to rise toward. Without forced circulation, astronauts would find themselves surrounded by a growing bubble of their own exhaled carbon dioxide and body heat, potentially suffocating even in an oxygen-rich atmosphere. To prevent this, fans circulate the air continuously, creating gentle breezes that keep the atmosphere well-mixed and comfortable. The fans run quietly, their white noise becoming a comforting background hum that astronauts report they eventually tune out, much like people living near a river stop noticing its constant murmur. The materials used in spacecraft construction are chosen with extraordinary care. Every component must withstand the extreme temperatures of space, from the intense heat of direct sunlight to the bone-chilling cold of shadow. They must resist degradation from radiation, including ultraviolet light from the sun and cosmic rays from deep space. They must maintain their properties in vacuum, where many materials outgas, releasing trapped air and sometimes decomposing. And they must do all of this while being as light as possible, because every ounce of mass requires fuel to launch into orbit. Aluminum alloys are common for spacecraft structures, providing excellent strength-to-weight ratios and good resistance to thermal cycling. Titanium is used where strength is critical and weight must be minimized. Composite materials, made from carbon fibers embedded in resin, offer even better performance, combining exceptional strength with incredibly low weight. These materials are carefully selected and tested, their properties measured and verified to ensure they'll perform as expected in the demanding environment of space. Multilayer insulation, often called MLI, wraps spacecraft in protective blankets that reflect heat and block radiation. These blankets consist of many thin layers of reflective film, typically made from aluminized mylar or captain, separated by lightweight mesh spacers. The layers create a barrier that's highly effective at preventing heat transfer, maintaining stable temperatures inside the spacecraft regardless of external conditions. MLI has a distinctive appearance, gold or silver and crinkly, giving spacecraft their characteristic shiny appearance. But beneath this flashy exterior lies a simple principle. Multiple thin barriers work better than one thick one, reflecting heat back and forth until it's finally radiated away into space. Solar panels provide the electrical power that spacecraft need to operate. Modern panels are marvels of efficiency, converting sunlight directly into electricity through the photovoltaic effect. Each panel consists of thousands of individual solar cells, silicon wafers that generate electrical current when photons strike them. The panels are mounted on booms or wings that can be rotated to track the sun, ensuring maximum power generation throughout the day. In low Earth orbit, the space station orbits through sunlight and shadow, experiencing dawn and dusk 16 times per day. The solar panels respond to these changes automatically, deploying during daylight periods and weathering the eclipse phases without complaint, ready to resume power generation when sunlight returns. Batteries store excess energy generated during sunlit portions of the orbit, then provide power during eclipse periods when the solar panels are in shadow. These batteries charge and discharge thousands of times over the life of a spacecraft, a demanding cycle that requires robust design and careful management. Modern lithium-ion batteries handle this challenge well, storing energy efficiently and releasing it smoothly, ensuring that spacecraft systems never experience power interruptions. The batteries work in parallel with the solar panels, accepting charge when available and delivering power when needed, all managed by computers that balance loads and optimize performance without human intervention. Propulsion systems on spacecraft come in many varieties, but all share a common principle. They expel mass in one direction to push the spacecraft in the other, Newton's third law in action. Chemical rockets, the workhorses of space propulsion, burn fuel and oxidizer to produce hot gases that expand through a nozzle, creating thrust. These systems can produce tremendous force for short periods, useful for launching into orbit or making major course changes. When a chemical rocket fires, it's a controlled explosion, but one that's directed and harnessed, providing precisely the amount of thrust needed for exactly the duration required. Electric propulsion systems, by contrast, work more gently but more efficiently. Ion engines accelerate charged particles to extremely high velocities using electromagnetic fields, creating a steady push that builds up over time. The thrust from an ion engine is tiny, roughly equivalent to the weight of a sheet of paper resting on your hand, but it can be sustained for months or even years. This patient approach to propulsion is ideal for deep space missions where there's no rush and efficiency matters more than raw power. The exhaust from an ion engine glows with an ethereal blue light, ionized xenon atoms streaming away at speeds exceeding 25,000 miles per second. A beautiful display of physics in action. All these systems work together to create an environment where humans can live and work in space, protected from the vacuum, maintained at comfortable temperatures and pressures, supplied with fresh air and clean water. The care that goes into designing these systems reflects our deep desire to explore space safely and sustainably. Each component is the result of careful thought and rigorous testing, designed not just to work but to work reliably for years in one of the most demanding environments imaginable. As you settle into sleep tonight, you can take comfort in knowing that this same care and attention protects every astronaut who ventures beyond Earth, keeping them safe in their journey through the peaceful void. Living in orbit, the peaceful rhythm of space stations. Life aboard a space station follows rhythms unlike anything experienced on Earth. A daily routine shaped by the unique environment of microgravity and the constant cycle of sunrise and sunset as the station orbits our planet. The International Space Station, humanity's home in the sky for the past 25 years, circles Earth every 90 minutes, traveling at 17,500 miles per hour, 250 miles above the surface. Despite this incredible speed, everything inside feels calm and still, the motion imperceptible to those aboard. Looking out the windows, Earth appears to turn slowly beneath you, continents and oceans drifting past in a mesmerizing display of blues, greens, and browns punctuated by swirling white clouds. Astronauts wake to an alarm each morning, though morning is an arbitrary designation when you experience 16 sunrises and sunsets every 24 hours. Their schedules are carefully planned to maintain a 24-hour day-night cycle, honoring the circadian rhythms embedded in human biology through millions of years of evolution. Without this structure, astronauts would quickly become disoriented, suffering from the space equivalent of perpetual jet lag. So they work and sleep to fixed schedules, beginning their day around 6 in the morning Greenwich Mean Time and ending it around 9:30 in the evening, with breaks for meals, exercise, and personal time. Sleep in microgravity is an unusual experience. Most astronauts use sleeping bags attached to the walls of small private sleeping compartments, though the orientation of these compartments is arbitrary. There's no up or down in space, so a wall becomes a floor simply by deciding it is. Astronauts slip into their sleeping bags and often assume a fetal position, the natural human posture in weightlessness. Some find this deeply comforting, reminiscent of the weightless months spent in the womb before birth. The sleeping bags prevent drifting, keeping astronauts in place while they rest. Ventilation is crucial during sleep because warm air doesn't rise in microgravity. Without airflow, an astronaut could find themselves surrounded by a bubble of their own exhaled carbon dioxide, which would lead to oxygen starvation and unpleasant wake-ups with splitting headaches. So sleeping compartments include ventilation fans that provide a gentle breeze, ensuring fresh air circulates around the sleeping astronaut. The sound of these fans, combined with the general background hum of station equipment, creates a constant white noise that some astronauts initially find disturbing, but most eventually find soothing, like sleeping next to a quietly running stream. Some brave souls experiment with floating free while they sleep, but this often results in collisions with equipment or being gradually pulled toward air intake vents by the airflow. Most astronauts prefer the security of being tethered in place, though they report dreaming of weightlessness, their sleeping minds incorporating the strange sensation of floating into vivid nocturnal adventures. Some use earplugs and eye masks to block out the noise and light, creating a darker, quieter environment more conducive to deep sleep. The morning routine begins with personal hygiene, which requires some adaptation to microgravity. There are no showers aboard the space station. Water doesn't fall in the absence of gravity, so traditional bathing is impossible. Instead, astronauts use wet towels to clean themselves, adding a small amount of water and soap to a towel and washing section by section. Surface tension keeps the water adhering to the towel and skin rather than floating away in droplets. For shaving, men apply water and shaving cream, which again sticks to the face through surface tension. They shave carefully, wiping the razor on a towel to clean it, the stubble and cream sticking to the towel until it's rolled up for disposal. Hair washing uses rinseless shampoo, originally developed for hospital patients unable to shower. Astronauts apply the shampoo to damp hair, work it into a lather, then wipe it away with a towel. The process isn't as satisfying as a hot shower, but it's sufficient to maintain hygiene and comfort. Brushing teeth is relatively straightforward. Astronauts can use regular toothpaste and toothbrushes, then either swallow the toothpaste or spit it into a towel. Water for drinking and washing comes from a dispenser that delivers controlled amounts, preventing the formation of loose droplets that could float around the cabin. Using the toilet requires more explanation and practice. The space station toilet uses airflow to replace gravity, with fans creating suction that pulls waste away from the body. Astronauts position themselves using leg restraints and handholds, ensuring a good seal between themselves and the toilet seat. Urine is collected through a funnel attached to a hose, with different adapters for men and women. The suction pulls the urine into a collection tank where it will later be processed and recycled into drinking water. Solid waste is similarly pulled away and stored in containers that are eventually loaded into cargo ships for disposal, burning up during atmospheric re-entry. Breakfast, like all meals on the station, is eaten from packages designed to keep food from escaping. Many foods are dehydrated and must be reconstituted with hot or cold water from a dispenser. Drinks come in pouches with straws, and the surface tension of the liquid keeps it from spilling even when the pouch is squeezed. More solid foods can be eaten with utensils, which have magnets to keep them attached to the dining table when not in use. Astronauts quickly learn to handle food with care, cutting it into bite-sized pieces and guiding it directly to their mouths to prevent fragments from floating away. The menu has evolved dramatically since the early days of spaceflight, when astronauts subsisted on barely palatable paste squeezed from tubes. Modern space food includes over 300 different items, from freeze-dried fruits and nuts that can be eaten directly to entrees that taste remarkably similar to their earthbound equivalents after rehydration and heating. There's even condiment dispensers for hot sauce, salt water, and pepper suspended in oil, because shaking traditional salt or pepper would create a floating cloud of seasonings that could clog equipment or irritate eyes and airways. Microgravity dulls the taste buds slightly, so astronauts often prefer spicier foods than they would on Earth. The lack of gravity also means that body fluids shift toward the head, creating a feeling similar to having a mild cold, which further diminishes taste and smell. Despite these challenges, mealtimes are social occasions where crew members gather to share food and conversation, maintaining the human traditions that make long-duration space flights psychologically sustainable. After breakfast, astronauts begin their scheduled work, which varies day by day depending on the current mission objectives. Some days are devoted to scientific experiments, taking advantage of the unique environment of microgravity to study phenomena impossible to observe on Earth. Flames burn differently in the absence of gravity, forming perfect spheres because there's no convective flow to pull hot gases upward. Fluids behave strangely, with surface tension effects dominating over gravity. Crystals grow larger and more perfectly formed when they don't settle under their own weight. Other days focus on maintenance, the endless task of keeping the station's systems functioning properly. Air filters must be cleaned or replaced. Equipment must be inspected and serviced. Software updates must be installed and tested. This work might seem mundane, but it's essential for survival. Every system has backups, and those backups have backups, but they must all be maintained to ensure they'll function if needed. Astronauts approach this work with patient professionalism, understanding that their lives depend on the reliable operation of station systems. Exercise occupies a mandatory 2.5 hours of each day, essential for maintaining muscle and bone strength in the absence of gravity. On Earth, bones and muscles work constantly to support the body's weight and enable movement against gravity's pull. In space, this load disappears, and without it, bones begin to lose calcium and muscles begin to atrophy. To prevent this, astronauts use specialized equipment. a treadmill with bungee cords to pull them down, providing the impact loading their bones need, a stationary bicycle for cardiovascular exercise, and resistance machines that use vacuum cylinders to create the feeling of lifting weights. The exercise sessions are often described as the hardest work astronauts do in space, but they're also important for psychological health. The physical exertion provides a release for stress and tension, and the endorphins produced during vigorous exercise help maintain mood and mental clarity. Some astronauts use this time to listen to music or watch videos from Earth, multitasking to make the exercise time more enjoyable. Free time is carefully protected in the crew schedule, recognizing that humans need periods of rest and recreation to maintain their mental health during long missions. Astronauts can spend this time however they wish. Reading books, listening to music, watching movies, or communicating with family and friends on Earth through email and occasional video calls. Internet access allows them to browse websites, check news, and stay connected with events on the planet below. But perhaps the most popular activity during free time is simply looking out the windows at Earth. The view from the space station is extraordinary, offering perspectives impossible to achieve any other way. Astronauts can watch thunderstorms marching across continents, their lightning flickering like strobes in the darkness. They can see the aurora borealis and aurora australis, shimmering curtains of green and red light that dance around the poles as charged particles from the sun interact with Earth's magnetic field. They can watch the Terminator, the line between day and night, sweep across the planet's surface, and they can see city lights twinkling like jewels scattered across the night-side continents. Many astronauts report experiencing what's called the overview effect, a profound shift in perspective that comes from seeing Earth as a whole. From space, our planet appears as a fragile sphere suspended in darkness, with no visible borders between nations and no sign of the conflicts and divisions that dominate terrestrial concerns. The thin blue line of the atmosphere looks startlingly delicate, a gossamer veil that protects all life on Earth from the harsh environment of space. This perspective often instills a deep sense of the interconnectedness of all humanity and the precious nature of our home world. The daily routine continues with more work, another meal, more exercise or experiments or maintenance, and eventually the evening wind-down period. Astronauts prepare for sleep by completing their hygiene routine, perhaps using wet wipes for a final wash, brushing their teeth, and changing into sleep clothes. They might spend a few minutes reviewing the next day's schedule or catching up on personal email. Then they retreat to their sleeping compartments, zip themselves into their sleeping bags, and let the gentle hum of the station's systems lull them towards sleep. Outside, Earth continues its eternal rotation, and the station continues its swift orbit. But inside, everything is peaceful and secure. The life support systems work tirelessly to maintain a comfortable environment. The solar panels rotate to track the sun, gathering energy. The computers monitor thousands of sensors, making tiny adjustments to keep all systems in balance. And the crew sleeps, their dreams perhaps filled with images of the beautiful blue planet turning slowly beneath them, a reminder of home and everything they're working to better understand and protect. The gentle journey, traveling through the cosmos. Space travel, despite its association with powerful rockets and dramatic launches, is fundamentally a patient endeavor characterized by long periods of quiet coasting punctuated by brief moments of activity. Once a spacecraft escapes Earth's gravity well, It enters a realm where motion continues indefinitely without resistance, where trajectories can be calculated with exquisite precision, and where the journey itself becomes a meditation on physics and persistence. The silence of space is profound and absolute. Sound requires a medium through which to travel, atoms or molecules that can vibrate and transfer energy from one location to another. In the vacuum of space, there are no molecules to carry sound waves, so there is no sound. Astronauts working outside their spacecraft in the emptiness of space experience a silence so complete that it can be disorienting. The only sounds they hear are those transmitted through their bodies or their spacesuits. Their own breathing, the hum of their life support systems, the voice of their colleague or mission control speaking through radio, conducted through the helmet's padding to their ears. This silence creates a sense of profound isolation, but also of peace. There's no traffic noise, no voices in the background, no mechanical sounds from distant equipment. Just perfect, unbroken quiet, as close to the absence of sensation as a human can experience while remaining conscious and aware. Some astronauts find this deeply calming, a reminder of how far they've traveled from the busy, noisy world below. Propulsion in space works on principles that seem almost magical but are actually straightforward applications of Newton's laws of motion. When a spacecraft expels mass in one direction, it must move in the opposite direction to conserve momentum. Chemical rockets do this by burning fuel and oxidizer, creating hot gases that expand through a nozzle and shoot out the back at tremendous velocities. The spacecraft moves forward as these gases rush backward, the forces perfectly balanced as dictated by the laws of physics. But here's where space travel becomes truly elegant. Once a spacecraft has achieved its desired velocity, the engines can be shut down completely. The spacecraft continues moving at the same speed and in the same direction, coasting through the void like a stone skipping across still water. This is orbital mechanics in its purest form, where motion persists without effort, where energy expended at the beginning of a journey carries you forward for months or years. Consider the Voyager spacecraft, launched in 1977 to explore the outer planets. After their initial boost from Earth and gravity assists from Jupiter and Saturn, both Voyager probes have coasted through space for decades with only occasional firings of their small attitude control thrusters. They're now beyond the edge of the solar system, still moving at tens of thousands of miles per hour through interstellar space, carried forward by the momentum imparted nearly 50 years ago. They will continue this journey essentially forever, becoming permanent ambassadors from Earth to the wider galaxy, traveling in silence and darkness long after all their systems have finally exhausted their power and fallen quiet. Navigation through space relies on precise knowledge of positions and velocities. Ground-based tracking stations around the world monitor spacecraft by sending radio signals and measuring the time delay of the return signal, determining distance with incredible accuracy. They also measure the Doppler shift of the radio signals, which reveals how fast the spacecraft is moving toward or away from Earth. From these measurements, navigation teams can calculate the spacecraft's trajectory with such precision that course corrections are measured in fractions of a meter per second. When corrections are needed, they're executed with patient care. Engineers calculate exactly when and in what direction to fire the engines, how much velocity to add or subtract, and what the resulting trajectory will be. These maneuvers are often called burns, even though modern propulsion systems are highly controlled and efficient. A typical course correction might involve firing the engines for just a few seconds or minutes, adding a small amount of velocity that gradually alters the spacecraft's path over the following days and weeks. For interplanetary missions, gravity assists provide an elegant way to change speed and direction without expending fuel. When a spacecraft approaches a planet on a carefully calculated trajectory, the planet's gravity pulls it in, accelerating it as it falls toward the massive body. If the spacecraft passes behind the planet relative to its direction of motion around the Sun, it can steal a tiny amount of the planet's orbital momentum, emerging from the encounter moving faster than it arrived. The planet's orbit is also changed, but by an amount so infinitesimally small as to be unmeasurable. This gravitational slingshot effect has been used on numerous missions, allowing spacecraft to reach distant destinations that would otherwise require impossibly large amounts of fuel. The Cassini spacecraft used gravity assists from Venus twice, then Earth, and finally Jupiter to reach Saturn, a journey that took 7 years but used far less fuel than a direct trajectory would have required. Each planetary encounter was a carefully choreographed dance, the spacecraft approaching at precisely the right angle and distance to achieve the desired velocity change. The planets, of course, continued on their eternal orbits, unperturbed by this fleeting interaction with humanity's messenger. Radiation protection is a significant concern for long-duration spaceflight. Space is filled with radiation. Particles accelerated to nearly the speed of light by supernovae and other cosmic events, streams of charged particles from the Sun, trapped radiation in planetary magnetospheres. This radiation can damage electronics and, more importantly, harm living tissue. Protecting against it requires careful spacecraft design and, for human missions, accepting some level of risk that's carefully monitored and managed. Spacecraft hulls provide some shielding simply through their mass. Radiation passing through matter is absorbed or deflected. Water and hydrogen-rich materials are particularly effective shields because they contain lots of nuclei for incoming radiation to collide with. Some spacecraft designs include water tanks positioned around crew compartments, providing both shielding and a useful resource. Other designs use layers of different materials, each chosen to stop or slow different types of radiation. For missions beyond low Earth orbit, solar flares present an acute danger. These explosions on the Sun's surface release massive amounts of radiation that stream through space at a significant fraction of the speed of light. While Earth's magnetic field deflects most of this radiation, spacecraft in deep space have no such protection. Mission planners monitor the Sun continuously, watching for signs of impending flares, and spacecraft include shielded compartments where crews can shelter during solar storms, waiting out the radiation like sailors in a storm cellar waiting for a tornado to pass. The psychological aspects of long-duration spaceflight present their own unique challenges. Being confined in a small space with the same few people for months or years, far from Earth and unable to return quickly if something goes wrong, places enormous stress on crews. Space agencies have learned through long experience that crew selection must consider not just technical qualifications but also psychological compatibility and resilience. Astronauts for long missions are chosen partly for their ability to remain calm under stress, to work cooperatively with others even in difficult circumstances, and to maintain their mental health through long periods of isolation and confinement. They undergo extensive training that includes isolation exercises, where they live together in confined simulated spacecraft for extended periods, learning to manage conflicts, maintain morale, and support each other through challenges. During actual missions, psychological support continues. Regular communication with family and friends helps maintain connections to Earth. Carefully planned schedules ensure adequate sleep, exercise, and recreation time. Crews celebrate birthdays and holidays, maintaining Earth traditions even in space. Mission Control provides news and updates from home, keeping crews informed about events in the world to which they'll eventually return. Some crews report that the shared experience of spaceflight creates bonds deeper than any they've experienced on Earth. Working together toward common goals, depending on each other for survival, experiencing the wonder of space together. These shared experiences forge connections that last lifetimes. Many astronauts remain close friends with their crew members long after their missions end, united by the understanding that only those who've been there can fully comprehend what it's like to live and work beyond the Earth. The duration of space journeys varies enormously depending on destination. A trip to the International Space Station takes just 6 hours from launch to docking, a quick commute by spacecraft standards. The Moon is 3 days away at typical spacecraft velocities. Mars, depending on where Earth and Mars are in their respective orbits, takes between 6 and 9 months to reach using current propulsion technology. These long journey times require careful planning and substantial life support resources. Everything astronauts will need must be carried with them or created from materials available on board. Water must be recycled with extraordinary efficiency. Air must be regenerated continuously. Food must be stored in forms that remain stable and nutritious for years. Spare parts and repair materials must be available for anything that might break during the mission. But perhaps the most important resource for long journeys is patience. Unlike Earth travel, where one can usually choose to stop, turn around, or take a different route if things aren't going well, space travel follows fixed trajectories determined by orbital mechanics. Once you've committed to a trajectory, you follow it to its conclusion. The laws of physics don't negotiate and they don't hurry. They simply are patient and implacable, and travelers through space must accept their terms. This enforced patience can actually be beneficial. It creates space for contemplation, for deep thinking, for appreciating the journey rather than focusing solely on the destination. Astronauts on long missions often report that they develop a different relationship with time, becoming less concerned with rushing through tasks and more focused on doing them well. They learn to find satisfaction in the daily routine, to appreciate small pleasures, to exist fully in each moment rather than constantly looking ahead to the next thing. The spacecraft becomes a small world unto itself during these long journeys, a bubble of life and warmth traveling through the cold void. Inside, systems hum and whir, maintaining the conditions necessary for survival. Outside, space stretches away in all directions, vast beyond human comprehension, dark and empty except for the distant points of starlight. The contrast is stark, but it's also comforting in its way. The spacecraft is a home, a shelter, a sanctuary from the hostile environment beyond its walls. And within its protection, humans can journey farther than any of our ancestors ever imagined, carried forward by patient momentum through the peaceful cosmic sea. Planetary destinations, peaceful harbors in space. Our solar system contains numerous destinations that future space travelers might visit, each offering unique landscapes and scientific opportunities. These worlds have waited in silence for billions of years, orbiting the sun in patient regularity, and they will continue their celestial dances long after humanity's first tentative visits. Let's explore these peaceful harbors in space, imagining what it might be like to set foot on surfaces where no human has yet walked. The Moon, Earth's closest celestial neighbor, remains the most accessible destination beyond our planet's atmosphere. It orbits Earth at an average distance of 238,855 miles, a journey of just 3 days for spacecraft traveling at typical velocities. The lunar surface is ancient and geologically quiet, having changed little over the past 3 billion years. Without atmosphere or weather to erode features, craters remain pristine for eons, their circular rims casting sharp shadows in the harsh sunlight. The lunar day lasts about 29.5 Earth days, with 2 weeks of continuous sunlight followed by 2 weeks of darkness. During the lunar day, temperatures at the equator can reach 240 degrees Fahrenheit, hot enough to boil water. During the lunar night, temperatures plummet to minus 280 degrees, approaching absolute zero. This extreme temperature range presents challenges for equipment and structures, but also offers opportunities for scientific research and resource utilization. At the lunar poles, conditions are different and potentially more hospitable for permanent settlements. Some craters near the poles are permanently shadowed, never receiving direct sunlight. These regions, called cold traps, contain water ice that has accumulated over billions of years from comet impacts and the solar wind. This ice represents a valuable resource for future lunar bases, providing water for drinking, oxygen for breathing when split by electrolysis, and hydrogen for rocket fuel. Meanwhile, nearby peaks and ridgelines receive almost constant sunlight, ideal locations for solar panels that could provide uninterrupted power. The Apollo astronauts who visited the Moon between 1969 and 1972 described it as peaceful and eerily beautiful. The lack of atmosphere meant perfect visibility to the horizon, with no haze to soften distant features. Colors were limited to blacks, whites, and grays, with occasional brown or orange tints in certain soils. The sky appeared completely black even during daytime because there's no atmosphere to scatter sunlight. Earth hung in this black sky, a brilliant blue and white sphere about 4 times larger in apparent size than the Moon appears from Earth. Walking on the Moon required adaptation to the lower gravity, just 1/6 that of Earth. Astronauts found they could easily carry heavy equipment that would be burdensome on Earth. They could jump higher and farther with less effort. But they also had to relearn how to move, developing a unique hopping gait that proved more efficient than trying to walk normally. The lunar soil, called regolith, is made of fine particles created by billions of years of meteorite impacts. It has unusual properties, sticking to everything it touches and compressing under footprints to create clear imprints that will persist for millions of years in the absence of wind or rain. Future lunar settlements might be built underground or in lava tubes. Natural tunnels formed billions of years ago when molten lava drained away from beneath solidified crusts. These tubes would provide natural protection from radiation and meteorite impacts while maintaining more stable temperatures than the surface experiences. Living spaces could be carved from solid rock or assembled from prefabricated modules, creating comfortable habitats insulated from the harsh lunar environment. Mars, the red planet, has long captured human imagination as a potential second home for humanity. It's much farther than the Moon, requiring a journey of 6 to 9 months depending on the relative positions of Earth and Mars in their orbits. But it offers something the Moon cannot: the possibility of eventual terraforming and the presence of resources needed to create a truly self-sustaining colony. Mars is cold, with average temperatures around -80 degrees Fahrenheit, though equatorial regions can reach a relatively balmy 70 degrees during summer days. The atmosphere is thin, less than 1% the density of Earth's, composed mostly of carbon dioxide with traces of nitrogen and argon. This thin atmosphere creates dust storms that can engulf the entire planet for months at a time, reducing sunlight and lowering temperatures further. Yet it's thick enough to create weather patterns, including water ice clouds, morning frosts, and seasonal dust devils. The Martian day, called a sol, lasts 24 hours and 39 minutes, remarkably similar to Earth's day. This coincidence would make adaptation easier for human settlers, allowing them to maintain something close to their natural circadian rhythms. The Martian year is nearly twice as long as Earth's, 687 Earth days, giving the planet pronounced seasons that manifest as polar ice caps that grow and shrink, changing the global atmospheric pressure as carbon dioxide freezes out at the winter pole and sublimes at the summer pole. Water on Mars exists primarily as ice, locked in the polar caps and buried in permafrost beneath the surface. Some evidence suggests that liquid water occasionally flows on the surface during warm seasons, though this remains controversial and is certainly not common. Ancient river valleys and lake beds show that Mars once had liquid water on its surface billions of years ago, when it was warmer and had a thicker atmosphere. What happened to that water and that atmosphere remains one of the great mysteries of planetary science, with implications for understanding Earth's own climate evolution. The Martian landscape is dramatic and varied. Olympus Mons, the largest volcano in the solar system, rises 16 miles above the surrounding plains, 3 times the height of Mount Everest. Its base covers an area roughly the size of Arizona. The volcano is so large that if you stood on its summit, its slopes would curve away beyond the horizon in all directions, giving no sense of standing on a mountain at all. The volcano is probably extinct, having last erupted millions of years ago, but its massive presence dominates the Tharsis region. Valles Marineris, a canyon system stretching over 2,500 miles along the Martian equator, dwarfs Earth's Grand Canyon. In places, it's 6 miles deep and 125 miles wide. Flying over this enormous rift valley would take hours, with its walls rising like mountain ranges on either side. The canyon probably formed through a combination of tectonic activity and erosion, though understanding its exact origin requires more study. The northern and southern hemispheres of Mars are strikingly different. The northern hemisphere consists mainly of low-lying smooth plains, possibly the floor of an ancient ocean that covered much of the northern third of the planet billions of years ago. The southern hemisphere is ancient cratered highlands, heavily pocked by impacts that occurred during the solar system's violent early history. The boundary between these regions, a kind of planetary coastline, can be traced around the planet, one of Mars's most intriguing features. Future Mars settlements would likely be built underground or under protective domes, shielding inhabitants from radiation and the occasional dust storm. The lower gravity, 38% of Earth's, would be noticeable but much easier to adapt to than the Moon's 1/6 gravity. Over time, settlers might terraform portions of Mars, thickening the atmosphere by releasing trapped gases, warming the planet using orbital mirrors or greenhouse gases, and eventually establishing ecosystems with plants and microorganisms that could begin producing oxygen. Venus presents a very different challenge. Often called Earth's sister planet because of its similar size and mass, Venus has evolved along a dramatically different path. Its surface temperature averages 860 degrees Fahrenheit, hot enough to melt lead, maintained by a runaway greenhouse effect where thick clouds of sulfuric acid trap heat radiating from the surface. The atmospheric pressure at the surface is 92 times that of Earth, equivalent to being 3,000 feet underwater. Yet Venus isn't entirely inhospitable. At an altitude of about 30 miles, atmospheric pressure and temperature become surprisingly Earth-like. The temperature hovers around room temperature, and the pressure equals sea level on Earth. This region, high in Venus's atmosphere, has been proposed as a location for floating cities suspended by balloons filled with breathable air, which would actually be a lifting gas in Venus's dense carbon dioxide atmosphere. Protected from the hellish surface conditions below, inhabitants of these cloud cities could conduct research and potentially extract resources from Venus's atmosphere. The outer solar system contains moons that may harbor subsurface oceans beneath icy crusts. Europa, orbiting Jupiter, is covered in water ice crisscrossed with dark streaks and ridges. Beneath this ice, kept liquid by tidal heating from Jupiter's immense gravity, may lie an ocean containing twice as much water as all of Earth's oceans combined. This ocean, if it exists, has existed for billions of years, raising the tantalizing possibility that life might have evolved there in the dark, warmed by volcanic vents on the seafloor, much like the life that clusters around deep-sea vents in Earth's oceans. Enceladus, a small moon of Saturn, actively vents water vapor and ice particles from fractures near its south pole, geysers that shoot hundreds of miles into space before falling back as snow or escaping into orbit around Saturn. These eruptions prove that Enceladus has a subsurface ocean and an energy source to keep it liquid. The Cassini spacecraft flew through these plumes, analyzing their composition and finding organic molecules and salts that suggest the ocean might be habitable. Titan, Saturn's largest moon, is the only moon in the solar system with a substantial atmosphere, actually thicker than Earth's, though composed mostly of nitrogen with methane and other hydrocarbons. Titan's surface, hidden beneath orange clouds, features liquid methane lakes and seas, river channels carved by methane rain, and dunes of hydrocarbon sand. The temperature is minus 290 degrees Fahrenheit, cold enough that water ice is as hard as granite, and methane cycles through the atmosphere as water does on Earth, evaporating, forming clouds, and falling as rain. Landing on Titan would be like arriving on a bizarro version of Earth, with familiar features like lakes, rivers, and rain, but composed of completely different substances. The thick atmosphere would support flight easily. A person wearing wings could fly in Titan's gravity and atmosphere with moderate effort. The low gravity, 1/7 of Earth's, combined with the thick atmosphere, would make movement easy and smooth. But the cold would be deadly without protection, and the atmosphere, while thick, is unbreathable, requiring a spacesuit or enclosed habitat. Each of these destinations offers unique opportunities and challenges. Some might host research stations inhabited by small teams of scientists for short periods. Others might eventually support permanent settlements with hundreds or thousands of residents. All of them expand the realm of human experience, offering new landscapes to explore, new phenomena to study, and new perspectives on our place in the cosmos. As you rest tonight, you can imagine future generations living and working on these distant worlds, building new homes under alien skies, continuing humanity's patient expansion through the solar system and perhaps eventually beyond. The comforting technology behind space travel. The technology that enables space travel is simultaneously incredibly complex and remarkably reliable, systems built with redundancy and fail-safes that would be considered excessive in almost any other application. This careful engineering reflects the high stakes of operating in the unforgiving environment of space, where a single failure could prove catastrophic. Yet this same dedication to reliability creates systems that are deeply trustworthy, machines that can be counted on to perform their functions year after year with minimal maintenance. Computers aboard spacecraft are marvels of rugged design, built to withstand radiation, extreme temperatures, and vibration while operating continuously for decades. Unlike consumer computers that might run for a few years before being replaced, spacecraft computers are designed for mission lifetimes measured in decades and must work without possibility of repair or upgrade once launched. This requirement has led to design philosophies that prioritize reliability over raw performance. Many spacecraft use radiation-hardened processors, chips manufactured with special techniques that make them resistant to the disruptive effects of cosmic rays and solar particles. These processors are often slower than commercial chips, sometimes running at speeds that seem ancient by consumer standards. The Curiosity rover on Mars, for instance, uses a processor running at just 200 megahertz, comparable to a computer from the 1990s. But this modest processor, built to survive Mars's harsh environment, has operated flawlessly since 2012, controlling the rover's movements and scientific instruments with patient reliability. Software on spacecraft is developed with extraordinary care, tested exhaustively before launch, and designed to handle unexpected situations gracefully. Multiple layers of checking verify that commands are valid before executing them. Watchdog timers reset systems that stop responding. Safe modes allow spacecraft to maintain basic functions even if primary systems fail, ensuring that ground controllers can diagnose and correct problems rather than losing contact permanently. The Voyager spacecraft provide a remarkable example of long-term reliability. Launched in 1977, both probes have operated for nearly 50 years, sending data from beyond the edge of the solar system using transmitters that produce just 23 watts of power, about the same as a refrigerator light bulb. Their computers have just 68 kilobytes of memory, thousands of times less than a modern smartphone, yet they continue executing their programs faithfully, managing instruments, pointing antennas toward Earth, and relaying measurements from their journey through the stars. Artificial intelligence is beginning to play a larger role in spacecraft operations, particularly for missions to distant destinations where communication delays make real-time control impossible. Mars rovers increasingly make their own decisions about where to drive and how to avoid obstacles, analyzing camera images to identify hazards and finding safe paths around them. The rover sends its planned route to Earth for approval, then executes it autonomously, stopping if it encounters anything unexpected and waiting for new instructions. Future spacecraft will use AI even more extensively, making complex decisions about scientific observations, resource allocation, and navigation without waiting for human input. But this AI isn't the science fiction version of conscious machines with their own agendas. It's narrow, specialized intelligence focused on specific tasks, using algorithms that have been thoroughly tested and validated. The goal isn't to replace human decision-making, but to extend it, allowing spacecraft to act on our behalf when we can't be there to guide them directly. Spacesuits are perhaps the most personal pieces of space technology, effectively single-person spacecraft that provide everything needed to survive in the vacuum. Modern spacesuits are sophisticated systems weighing about 300 pounds on Earth, though weightless in space, containing layers of materials that provide pressure, thermal control, radiation protection, and micrometeorite resistance. The suit maintains an internal pressure of 4.3 pounds per square inch, about 30% of sea-level atmospheric pressure on Earth. This lower pressure is a compromise between comfort and mobility. Higher pressures would make the suit too stiff to move in. To prevent decompression sickness from the reduced pressure, astronauts pre-breathe pure oxygen for hours before spacewalks, purging nitrogen from their bloodstream. Temperature control in spacesuits uses a network of water-filled tubes woven into the undergarment worn against the skin. Water circulates through these tubes, absorbing body heat and carrying it to a sublimator, a device where the water evaporates directly into space, carrying away heat. This system can handle the substantial heat load generated by an astronaut working hard in the suit, keeping them comfortable even during strenuous activities. The suit's life support system, worn as a backpack, provides oxygen, removes carbon dioxide, controls temperature, manages water for cooling and drinking, and powers all the suit systems. It's designed to support an astronaut for up to 8 hours, with additional reserves for emergencies. Every component is built with redundancy. If the primary oxygen supply fails, there's a backup. If communications fail, there are backup channels. If the cooling system fails, the astronaut can survive long enough to return to the safety of the spacecraft. Spacewalking, officially called extravehicular activity, is described by astronauts as simultaneously exhilarating and serene. Moving in the bulky suit requires effort and planning. Each movement must be deliberate and controlled. But once positioned at a work site, tethered to handholds with safety cables, astronauts report a sense of calm focus. The work often requires patience, manipulating tools with gloved hands that reduce tactile feedback, but there's deep satisfaction in accomplishing tasks in this unique environment. The view during spacewalks is extraordinary. Without a spacecraft's window frame to limit the field of view, astronauts see space all around them, a 360-degree panorama. Earth fills much of the sky, close enough that features like mountains and clouds are visible. Beyond Earth, the black of space and the bright points of stars create a backdrop that never grows old despite hours of exposure. Recycling systems on spacecraft represent closed-loop life support taken to its logical conclusion. Water is recovered from every possible source. Humidity condensed from the air, urine purified through multiple stages of filtration and processing, even the moisture in exhaled breath. On the International Space Station, these systems recover about 93% of the water aboard, turning waste into potable water that meets all standards for cleanliness and purity. The water recovery system uses multiple processing steps to ensure complete purification. Urine first passes through a distillation system where it's heated and evaporated, leaving contaminants behind. The water vapor is then condensed back into liquid, already much purer than it started. This water goes through filters that remove any remaining organic compounds and ions, then passes under UV light that kills any microorganisms that might have survived. Finally, the water is tested to verify it meets all quality standards before being released into the potable water supply. Oxygen generation through water electrolysis is remarkably simple in principle but sophisticated in implementation. Water is split into hydrogen and oxygen using electrical current passed through it. The oxygen is released into the cabin atmosphere, while the hydrogen is either vented overboard or reacted with carbon dioxide to produce water and methane, with the water being recovered and the methane vented. This Sabatier reaction closes the loop further, recovering oxygen from the carbon dioxide astronauts exhale rather than simply scrubbing it from the air and disposing of it. Emergency systems on spacecraft are designed to handle any conceivable problem with multiple layers of backup. Fire detection and suppression systems can identify and extinguish flames quickly, crucial in the confined space of a spacecraft where smoke and toxic fumes have nowhere to escape. Pressure leak detectors can identify breaches in the hull, and crew members can close hatches to isolate the affected section while they work to patch the leak. Medical emergencies are handled with equipment and training that allow crew members to provide care for a wide range of conditions. Medications, diagnostic equipment, and even minor surgical instruments are available aboard the space station. Astronauts receive extensive medical training before their missions, learning to handle injuries and illnesses that might occur when professional medical help is hours or days away. Ground-based flight surgeons can provide guidance via communication links, reviewing medical data and helping diagnose conditions, but ultimately the crew must be able to handle most situations independently. The return to Earth is perhaps the most technologically demanding phase of any space mission. Spacecraft must shed the tremendous velocity they've accumulated, over 17,000 miles per hour for vehicles in low Earth orbit, and do so without burning up from the friction with the atmosphere. Heat shields protect spacecraft during this fiery descent, materials that gradually ablate, carrying away heat as they vaporize. Parachutes slow the final descent, deploying in stages. Small drogue chutes first to stabilize the spacecraft and slow it to speeds where larger main parachutes can safely deploy. These main parachutes, often among the largest ever made, bring the spacecraft down to speeds slow enough for a relatively gentle landing. Russian Soyuz spacecraft used last-second retro rockets to cushion the final touchdown, firing just before impact to reduce the landing speed to a few miles per hour. Recovery teams stand ready to reach returning spacecraft quickly, providing medical assistance to crew members who've spent months adapting to microgravity and now must readjust to Earth's full gravity. The disorientation and weakness that follows long-duration spaceflight is temporary, with most astronauts recovering their full strength within weeks through carefully managed exercise and rehabilitation. All of this technology, from computers to spacesuits to life support systems, exists to enable human beings to explore beyond Earth safely. Each component reflects years of development, testing, and refinement. Each system incorporates lessons learned from previous missions, and each new mission adds to our knowledge, improving designs and procedures for future explorers. The result is a collection of technologies that, while complex, inspire confidence through their demonstrated reliability and the care with which they're maintained and operated. As you rest tonight, you can trust that these same technologies protect and support astronauts in space right now, performing their functions with quiet competence while humanity's representatives continue their work among the stars. The human spirit in space, cooperation and peace. Perhaps the most remarkable aspect of space travel isn't the technology or the science, but the human cooperation it has inspired. Space is too difficult, too expensive, and too dangerous for any nation to explore alone. Success requires sharing knowledge, pooling resources, and working together despite political differences and cultural barriers. The International Space Station exemplifies this cooperation, a project involving the United States, Russia, Canada, Japan, and the European Space Agency, representing 15 European nations. The station's very structure embodies international collaboration. Russian modules provide propulsion and life support. American modules house laboratories and connecting nodes. Japanese and European laboratories contribute specialized research facilities. Canadian robotic systems allow external maintenance and construction. Each nation built its contributions according to agreed standards, ensuring they would fit together and work as an integrated whole despite being constructed on opposite sides of the world. Crews aboard the station are deliberately international, with astronauts and cosmonauts from different nations living and working together for months at a time. They communicate in English and Russian, often mixing both languages in technical discussions. They share meals, celebrate each other's holidays, and form friendships that transcend national boundaries. When political tensions rise on Earth, these personal relationships help maintain the collaborative spirit that keeps the station functioning. This cooperation wasn't always easy to achieve. The space race began as competition, nations trying to best each other in achievements and firsts. The United States and Soviet Union competed to launch the first satellite, put the first person in space, complete the first spacewalk, and land the first humans on the moon. Each achievement was tallied as a victory in the Cold War, used for propaganda purposes and national pride. But gradually, this competition evolved into cooperation. The Apollo-Soyuz test project in 1975 brought together American astronauts and Soviet cosmonauts in orbit, their spacecraft docking together for 2 days of joint activities and experiments. It was a symbolic moment, showing that even during the Cold War, space could be a realm of peace and cooperation. The astronauts and cosmonauts exchanged gifts, shared meals, and conducted experiments together, demonstrating the possibilities for future collaboration. When the Cold War ended, cooperation accelerated. Russia joined the space station program, contributing modules and Soyuz spacecraft that became the primary means of reaching the station after the space shuttle retired. This partnership required trust on both sides, with the United States depending on Russian rockets and spacecraft for access to their own laboratory in space. The relationship has endured despite occasional political tensions, a testament to the power of shared goals and mutual respect among the space agencies and astronauts involved. Astronaut selection has evolved to recognize that long-duration spaceflight requires more than technical skills and physical fitness. Psychological compatibility, emotional stability, and the ability to work cooperatively under stress are equally important. Space agencies look for people who can maintain their performance under pressure, adapt to changing circumstances, resolve conflicts constructively, and support their crewmates through difficulties. The training process for astronauts takes years and covers an enormous range of skills. Astronauts must learn the systems of the spacecraft and space station in exhaustive detail, understanding not just how to operate them but how they work and how to troubleshoot problems. They train underwater in neutral buoyancy facilities, practicing spacewalks in conditions that approximate weightlessness. They fly in aircraft that create brief periods of microgravity, learning to move and work in that unfamiliar environment. They learn survival skills for emergency landings in remote locations, medical procedures for treating injuries in space, and languages to communicate with international partners. Perhaps most importantly, they learn to work as a team. Training exercises emphasize cooperation, communication, and mutual support. Astronauts practice making decisions under stress, managing emergencies, and supporting each other through setbacks and challenges. They spend time together in isolation, living in confined spaces to simulate the conditions they'll face in space, learning each other's personalities, strengths, and weaknesses. The psychological challenges of spaceflight are substantial and shouldn't be underestimated. Being confined in a small space with limited privacy, far from family and friends, unable to go outside or experience Earth's natural environment. These conditions strain mental health even for well-adjusted individuals. Add the stress of knowing that your survival depends on the proper functioning of complex equipment and the competence of your crewmates, and the psychological demands become clear. Space agencies provide substantial psychological support for crews. Before launch, astronauts work with psychologists to develop coping strategies and identify potential stressors. During missions, they have regular private conferences with psychological support personnel on the ground, opportunities to discuss concerns and receive guidance. They can communicate with family and friends through email and scheduled video calls, maintaining connections that help them feel less isolated. Mental health in space is also supported through environmental design. The space station includes windows that provide views of Earth, proven to have positive effects on mood and mental well-being. Crews are encouraged to take photos and spend time simply looking out at the planet, experiencing the beauty and tranquility of that perspective. Personal items are allowed aboard, small mementos and photos that provide comfort and connection to life on Earth. Some astronauts practice meditation or mindfulness techniques, finding that these practices help manage stress and maintain psychological balance. The regular schedule of work, exercise, and sleep helps maintain structure and normalcy. And the shared experience of spaceflight creates strong bonds between crew members, friendships forged through shared challenges and mutual dependence. Many astronauts report experiencing what's called the overview effect, a cognitive shift that results from viewing Earth from space. Seeing the planet as a whole without visible borders emphasizes the interconnectedness of all humanity and the fragility of our biosphere. The thin blue line of the atmosphere appears startlingly delicate from space, a reminder that this narrow shell of air is all that protects life from the hostile void. Astronauts often describe this perspective as profoundly moving, even spiritual. They speak of seeing Earth as a unified whole, a beautiful blue marble floating in darkness, and feeling a deep sense of responsibility to protect it. They note that from space, the things that divide humanity on the surface, borders, religions, politics, all become invisible and seemingly unimportant compared to our shared humanity and common home. This perspective has inspired many astronauts to become advocates for environmental protection, peace, and international cooperation after returning to Earth. They speak at schools and conferences, sharing their experiences and the insights gained from that unique vantage point. They work to inspire the next generation to pursue careers in science and engineering, to continue humanity's exploration of space, and to use the technology and knowledge gained from space exploration to better life on Earth. The peaceful nature of space exploration extends to the legal framework that governs it. The Outer Space Treaty, signed in 1967, establishes that space shall be free for exploration and use by all nations, that celestial bodies cannot be claimed as national territory, and that space shall be used for peaceful purposes. Nuclear weapons and other weapons of mass destruction are banned from orbit and from celestial bodies. The treaty has been ratified by over 100 nations and has been remarkably successful in keeping space a realm of peace and scientific cooperation. This legal framework reflects a recognition that space is too important and too challenging to be divided into competing territories or turned into another battlefield. The vast scale of space and the difficulties of operating there encourage cooperation rather than competition. Nations that might be rivals on Earth find common ground in their space programs, working together because the benefits of cooperation far exceed the potential gains from competition. Looking forward, space exploration will continue to require and foster international cooperation. Plans for returning to the Moon under the Artemis program involve not just NASA but also space agencies from Europe, Japan, Canada, and many other nations. Each brings unique capabilities and expertise, contributing to a collective effort that will establish a permanent human presence beyond Earth. The Artemis Accords, signed by over 50 countries, establish principles for peaceful cooperation in space exploration, building on the foundation of the Outer Space Treaty. The spirit of cooperation extends beyond governments to include private companies developing new spacecraft and technologies. Commercial spaceflight companies work alongside national space agencies, contributing innovation and efficiency while benefiting from the experience and oversight of established organizations. This blend of public and private effort, international partnership, and national capability creates a robust ecosystem for space exploration that's more resilient and sustainable than any single entity could achieve alone. As you drift towards sleep tonight, you can take comfort in knowing that humanity's journey into space is fundamentally a peaceful one, driven by curiosity and cooperation rather than conflict. The technologies being developed, the partnerships being forged, and the knowledge being gained all serve to benefit everyone on Earth, regardless of nationality or background. Space exploration shows us at our best, working together to achieve the seemingly impossible, extending our reach beyond our home planet while maintaining the values that make us human. The stars await, and we will reach them together, step by patient step, carried forward by our shared dreams and determination. The future of space travel, a gentle unfolding. The future of space travel is unfolding before us, not with sudden dramatic leaps, but with steady, patient progress as each new capability builds upon the last. Looking ahead, we can see the outlines of missions that will carry humans farther from Earth than we've ever traveled, establish permanent settlements on other worlds, and perhaps eventually venture beyond our solar system to touch the stars themselves. These achievements won't happen overnight. They'll emerge gradually through decades of careful development, but their inevitability becomes clearer with each passing year. NASA's Artemis program represents the current frontier, aimed at returning humans to the moon for the first time since 1972. Unlike Apollo, which demonstrated that lunar landing was possible before stepping back, Artemis aims to establish a sustained presence that will serve as a stepping stone to Mars and beyond. The program includes plans for the Artemis base camp near the lunar South Pole, where astronauts will live and work for missions lasting up to 2 months. The lunar South Pole is particularly attractive because permanently shadowed craters there contain water ice that has accumulated over billions of years. This water represents a precious resource that can be split into hydrogen and oxygen for rocket fuel, reducing the amount of supplies that must be launched from Earth. Nearby mountain peaks and ridge lines receive almost constant sunlight, ideal locations for solar panels that could provide continuous power. These geographical features make the South Pole region perfect for establishing humanity's first permanent off-world settlement. The Artemis program also includes the Lunar Gateway, a small space station that will orbit the moon, serving as a staging point for lunar surface missions and a testbed for technologies needed for Mars exploration. Gateway will be much smaller than the International Space Station, designed to support crews of 4 for missions lasting 1 to 3 months. Its orbit will allow it to serve both lunar operations and deep space missions, making it a versatile platform for multiple purposes. Commercial partners play a crucial role in Artemis. Companies are developing lunar landers that will carry astronauts from Gateway down to the surface and back. These human landing systems must be capable of precise landings on challenging terrain, reliable operation in the harsh lunar environment, and safe return of crews to orbit. The development of these systems by multiple companies creates redundancy and drives innovation through competition. In 2026, Artemis II will send 4 astronauts on a trip around the moon, testing the Orion spacecraft and Space Launch System in a crewed mission for the first time. These astronauts will venture farther from Earth than any humans since Apollo 17, over 238,000 miles from home. They won't land on the moon. Instead, they'll orbit it, verifying that all systems work as designed and preparing the way for Artemis III, which aims to land astronauts at the lunar South Pole. Commercial lunar exploration is proceeding in parallel with government efforts. Multiple companies are developing robotic landers under NASA's Commercial Lunar Payload Services program, delivering scientific instruments and technology demonstrations to the lunar surface. Blue Origin, Firefly Aerospace, Intuitive Machines, and Astrobotic have all developed or are developing lunar landers, creating a growing fleet of commercial spacecraft capable of reaching the moon. These commercial missions serve multiple purposes. They deliver scientific instruments for NASA and other customers, test technologies that will be needed for future missions, and begin to establish a lunar economy where companies can sell transportation and services to multiple customers. As the cost of lunar access decreases and reliability increases, more customers will emerge, creating a self-sustaining market that doesn't depend entirely on government funding. Mars remains the ultimate goal for many in the space community, the destination that captures imaginations and drives long-term planning. Getting humans to Mars and back safely represents an enormous challenge, requiring technologies and capabilities that don't yet exist. The journey takes 6 to 9 months each way using current propulsion systems, meaning any Mars mission will last at least 2 years from Earth departure to return. During much of this time, communication with Earth will be delayed by light travel time, as much as 22 minutes when the planets are at their farthest separation. These constraints mean that Mars crews must be largely self-sufficient, able to handle emergencies and make decisions without real-time support from Earth. They'll need robust life support systems capable of operating reliably for years, extensive medical capabilities to handle injuries and illnesses, and psychological support systems to maintain crew health through the isolation and confinement. The spacecraft itself must be large enough to provide adequate living space, shielded sufficiently to protect against cosmic radiation, and equipped with backup systems for every critical function. Various concepts have been proposed for Mars missions, each with different approaches to solving these challenges. Some envisions building the Mars spacecraft in lunar orbit, using resources from the Moon to reduce launch costs from Earth. Others propose nuclear thermal propulsion, which could cut journey times in half by providing more efficient thrust than chemical rockets. Still others suggest sending cargo ahead on slow trajectories, prepositioning supplies at Mars before the crew departs. What all these plans share is patience and methodical progression. Each mission to the Moon teaches lessons that apply to Mars. Each technology developed for lunar operations, from life support systems to habitat construction to resource utilization, provides capabilities that will be needed on the Red Planet. The Gateway Station serves as a proving ground for deep space operations, testing equipment and procedures in an environment where Earth is still close enough for emergency return if needed. Private companies are also developing Mars mission concepts. SpaceX's Starship, a fully reusable Super Heavy launch vehicle, is being designed with Mars colonization as its ultimate goal. The company envisions fleets of starships traveling to Mars during favorable launch windows, carrying both cargo and crew to establish a self-sustaining settlement. This ambitious vision faces numerous technical challenges, from in-orbit refueling to landing safely on Mars with heavy payloads. But the company is working through these problems methodically, testing components and gathering data with each flight. The possibility of human settlement on Mars raises fascinating questions about long-term adaptation to that environment. Mars's gravity is 38% of Earth's, stronger than the Moon's 1/6, but still significantly less than what our bodies evolved to handle. Over generations, might people born and raised on Mars develop differently, their bodies adapting to the lighter gravity? Would they eventually find Earth's stronger gravity oppressive, preferring to remain on their adopted home world? These questions remain theoretical for now, but they hint at a future where humanity becomes a multiplanetary species, with populations adapted to different worlds. Children born on Mars would be the first true Martians, their entire lives spent under red skies, their worldview shaped by a planet that's both harsh and beautiful in ways that Earth isn't. They would grow up knowing Earth only through videos and virtual reality, a distant blue sphere where their species originated but which they might never visit. Space tourism is beginning to emerge as an industry, with several companies offering flights to the edge of space or to orbit. These early offerings are expensive, accessible only to the very wealthy, but costs are expected to decrease as launch systems become more reusable and operational experience grows. The long-term vision includes orbital hotels where tourists can experience weightlessness and view Earth from space, lunar flybys that offer views of the far side, and eventually stays at lunar surface facilities. The impact of space tourism on public perception could be significant. As more people experience spaceflight personally, space becomes less abstract and more real, a destination rather than just a frontier. Those who've seen Earth from space often return with changed perspectives, a deeper appreciation for our planet's beauty and fragility. If thousands or eventually millions of people gain this perspective through tourism, it could influence how humanity addresses global challenges like climate change and resource management. Interstellar travel, journeys to the stars themselves, remains firmly in the realm of distant future speculation. The nearest star system, Alpha Centauri, is over 4 light-years away, meaning that even traveling at 1/10 the speed of light would require over 40 years to reach it. Achieving such velocities with current propulsion technology is impossible. The amount of fuel required exceeds any practical limit. New approaches like nuclear fusion drives, antimatter engines, or even exotic concepts like solar sails pushed by powerful lasers would be needed. Various concepts have been explored theoretically, from generation ships that would travel for centuries with rotating crews to sleeper ships where crews spend the journey in suspended animation. Some proposals involve sending only robots and artificial intelligence, establishing self-replicating factories at destination stars to build infrastructure before humans arrive. Others suggest that consciousness itself might be transmitted, with human minds encoded as information and broadcast to distant receivers where they could be instantiated in robotic or cloned bodies. These ideas remain speculative, but they capture the human impulse to explore, to see what lies beyond the next horizon. Even if interstellar travel proves impossible or impractical, contemplating it stretches our thinking and sometimes leads to insights applicable to nearer-term challenges. The technologies needed for interstellar flight, things like closed-loop life support and multi-generational spacecraft operation, have applications in establishing permanent settlements in our own solar system. The timeline for these developments extends across decades and centuries. Lunar bases might be established within the next 10 to 20 years. Mars missions could launch in the 2040s or 2050s, with permanent settlements potentially following by the end of this century. Beyond that, asteroid mining, settlements on the moons of Jupiter and Saturn, and exploration of the outer solar system could occupy the 22nd century and beyond. Each step will be taken carefully, with extensive testing and preparation before committing to irreversible decisions. Spaceflight has always progressed this way, through patient accumulation of knowledge and capability, each mission building on the lessons of previous ones. There will be setbacks and failures along the way. Space is unforgiving of mistakes, and ambitious undertakings sometimes don't succeed on the first attempt. But the overall trajectory is clear. Humanity is becoming a spacefaring species, expanding our presence beyond Earth in a process that will continue for as long as our civilization endures. The motivation for this expansion is multifaceted. Scientific curiosity drives us to explore and understand new environments. Economic interests see opportunities in space resources and industrial processes. Strategic concerns suggest that a multiplanetary species is more resilient than one confined to a single world. And deeper human drives, the same impulses that sent our ancestors exploring across continents and oceans, pull us toward new frontiers and unknown horizons. But perhaps the most compelling reason is simply that space is there, vast and mysterious and waiting. The peaceful void holds wonders we can barely imagine, phenomena we've never observed, knowledge we haven't yet conceived. Every question we answer about space raises new questions, deeper and more intriguing than before. The process of exploration is endless, a journey that has no final destination but rather continues forever, each discovery opening new avenues for investigation and understanding. As you rest tonight, you can imagine that future unfolding slowly and inevitably, each day bringing small steps toward larger goals. Somewhere, engineers are designing spacecraft systems. Scientists are analyzing data from space telescopes and planetary probes. Astronauts are training for upcoming missions. And in quiet labs and workshops around the world, people are solving problems and developing technologies that will someday carry humanity to destinations we haven't yet imagined. The future of space travel is peaceful and patient, built on cooperation and careful progress. It unfolds in its own time, neither rushed nor delayed, following the logic of orbital mechanics and technological readiness. And it invites all of humanity to participate, whether directly through working in space industries or indirectly through supporting exploration, sharing in the discoveries, and taking pride in what our species can achieve when we work together toward common goals. The stars await, and we will reach them, step by gentle step, carried forward by our curiosity and determination into the infinite peaceful night. As our journey through the peaceful aspects of space travel comes to a close, let's take a moment to reflect on everything we've explored together. We've traveled from the quiet dreams of early pioneers like Tsiolkovsky and Goddard, through the methodical development of rockets and spacecraft, to the present day where humans live and work continuously in orbit aboard the International Space Station. We've seen how spacecraft are designed with elegant simplicity to function in the vacuum of space, how life support systems maintain comfortable environments through closed-loop recycling, and how propulsion systems work patiently to navigate across vast distances. We've explored the daily rhythm of life in space, the routines that astronauts follow to maintain their physical and mental health during long missions. We've seen how international cooperation has made possible achievements no single nation could accomplish alone, creating partnerships that transcend political boundaries and demonstrate humanity at its best. We've imagined visiting other worlds in our solar system, from the moon's ancient, quiet surface to Mars's dramatic landscapes, from the ice-covered oceans of distant moons to the exotic environments of planets we can barely comprehend. And we've looked ahead to a future where humanity gradually expands through the solar system and perhaps eventually beyond, establishing permanent settlements on other worlds and continuing the great journey of exploration that has characterized our species since the beginning. This future unfolds slowly and peacefully, each generation building on the achievements of the last, extending our reach a little farther, learning a little more, growing gradually into our role as a spacefaring civilization. Throughout this exploration, certain themes have emerged repeatedly. The patience required for space travel, where journeys take months or years and preparations take decades. The elegance of the engineering solutions that enable survival in hostile environments. The cooperation between nations and organizations working toward shared goals. And the profound perspective that comes from seeing Earth from space, recognizing our planet as a precious, fragile home that deserves our care and protection. Space travel shows us what humans can achieve through dedication and teamwork. It demonstrates that seemingly impossible challenges can be overcome through patient effort and careful planning. And it offers hope for the future, showing that we can work together peacefully to accomplish extraordinary things. As you drift deeper into sleep, let these thoughts comfort you. Know that right now, at this very moment, the International Space Station is passing overhead, astronauts from different nations working together in orbit. Solar arrays are rotating to track the sun, life support systems are humming quietly, and Earth is turning slowly beneath them, a beautiful blue sphere suspended in darkness. If you've enjoyed this journey through the peaceful aspects of space travel, please consider subscribing to the Deep Science Sleep channel and clicking the like button. Your support helps us continue creating content that explores the wonders of science in ways that are both educational and relaxing. Share these videos with friends who might enjoy learning while they drift off to sleep, and let us know in the comments what other topics you'd like us to explore. Thank you for joining me on this voyage through the cosmos. May your dreams carry you to distant stars, and may you wake refreshed and ready to face whatever challenges tomorrow brings. Sleep well, knowing that humanity continues its patient journey outward, exploring the peaceful depths of space, one careful step at a time. Good night.